Hello, my name is John Hedengren, and I'm a professor at Brigham Young University, and I'll be talking today about physics-informed deep learning for prediction of thermophysical properties, and in particular, focusing on normal boiling point. Now, one of the concerns that several have had about machine learning and deep learning is its ability to extrapolate. And so we're going to be talking about thermophysical properties, being able to predict new compounds and their thermophysical properties based on a training set of other compounds. Now, one of the things that we're going to be adding to this is physics-informed information to help guide the extrapolation. So, accurate thermophysical properties are crucial to all aspects of chemical engineering, whether you are designing a new distillation column or a new reactor, or other type of equipment where you're trying to understand maybe the pressure versus temperature or other aspects of the process. So it's used in many process simulators. You also have, in addition to process simulators, you might need to design or operate that reactor or that distillation column based on those thermophysical properties. So let's talk about some of the constant properties. So these are not dependent on temperature, and there are 32 constant properties that are tracked in the DIPPR database that covers about 16 to 1700 compounds, and each of these are important. Some of them are easy, such as molecular weight. Others of them, such as melting point, you need to be able to take a pure compound and be able to get it down to its freezing point and be able to measure that experimentally. Okay, we also have others like 15 temperature dependent properties as well. And each of these are going to have a temperature dependence, okay, either increase or decrease with temperature. And so here is our property. So we not only have a constant property, but that we need to be able to track how that changes with temperature. So the DIPPR 801 database, two things that are very important there are accuracy and be able to quantify for those compounds how much accuracy is there with that prediction or measurement. Also completeness. Be able to have all of these temperature independent and temperature dependent properties for all of the compounds in the database. So let's just talk about also some of the current members that are supporting this. This was founded in 1980, and this has a support of all of these member companies that all participate and are interested in this database of values that can be used in their processes. So let's just take a look at some of the structural information that's available between these different properties. So we have, for example, this Clapeyron equation, and we have dP, the saturation pressure, vapor pressure, and also the heat of vaporization, and then also the liquid density. And we might have measurements for each of these. Okay, and one of the things that's been done in developing this database is taking measured points for each of these, in this case, vapor pressure, liquid density, and then heat of vaporization. And the question is, if you have two conflicting data sets, for example, which one do you trust? Do you trust the orange ones or do you trust the blue ones? Because it looks like they differ in this region. And so one of the strategies with this is to use equations such as the Clapeyron equation, some of this more fundamental information about the molecules or about the relationship between these properties that you can use to help fill in the database with values. So in this case, we would want to use the relationship between the vapor pressure, the heat of vaporization, and then also the liquid density to be able to understand that these points should potentially be rejected in favor of trusting the blue points, for example. Okay, so systems approach, there's actually quite a bit of fundamental or physics-based information that's available with all of these properties. The blue lines are relationships that have known fundamental equations that relate those two. And the red ones are more theoretical. Okay, so for example, the heat of vaporization and the vapor pressure, like we talked about with the Clapeyron equation. All right, and then you have another one like critical volume and liquid density, where there's more of a simulated or theoretical relationship between those two. But you can see with all of these here on this that there are many relationships between them that can help us optimize and be able to select which data is good and which data is not. We want to be able to use some of this physics-based information in training deep learning to be able to predict properties as well. Okay, so let's just look at some of the examples here. If I give you a little bit of background to put some things in perspective. We're great at predicting some properties, but bad at others. We try to use all the methods possible when evaluating the compounds. Here's an example with liquid viscosity. We tested the best current prediction methods for just low molecular weight nonpolar compounds against data in the DIPPR database. There are compounds that should be easy to predict, as there are normal carbon, hydrogen, and halogen compounds. But the best that can be done on average is 2%, and even when there are a lot of random outliers with big errors. For example, 10% of the compounds in the Sastry method had errors greater than 100%. We need better predictions for many properties. So almost all property prediction methods currently used by DIPPR and similar projects fall into one of three categories: group contribution, corresponding states, and QSPR methods. Group contribution methods break the molecule up into functional groups which contribute to different amounts to the property. QSPR approaches calculate various molecular level descriptors of a molecule and try to correlate these to the properties. Thousands of descriptors have been proposed, and obvious ones include things like molecular weight, van der Waals area or volume, radius of gyration, and various branching pathways. Corresponding states approaches try to correlate properties to reduce temperature, pressure, volume, and eccentric factor. They may also use other data or QSPR descriptors such as radius of gyration or dipole moment. What we found, though, is that we seem to have reached the limit of such approaches in terms of prediction improvement. So we have now moved on to machine learning approaches. But as you may know, reproducibility of machine learning AI approaches is a problem. Moreover, traditionally such approaches don't extrapolate well for situations outside the training set. The methods produced don't seem to suffer as much with extrapolation because we're using some physics in creating the technique. So our approach to machine learning is to incorporate physics-based constraints into the algorithm during the fitting process to improve predictive performance. So let's just talk about one simple example with Parachor prediction. We can see the equation here. Oh, let me come back here to the equation. Okay, so here's our Parachor prediction, where the Parachor value here relates the liquid density, the difference between the liquid and the vapor density, multiply it by the Parachor value, take it to the fourth power to be able to predict surface tension. So several group contribution methods have been developed over the years to predict Parachor so that surface tension and diffusivities can be predicted. So one of these was Garagesi and co-workers developed a neural network to predict the property. The features they provided to the algorithm were functional groups such as number of the CH3 groups in the molecule. They were able to develop a method. The results of each of the groups, some of them have negative contributions. So why is that important? The Parachor is sort of a volume parameter. As you add atoms to construct a molecule, the Parachor grows. From a physical standpoint, it doesn't make sense that a contribution should be negative. This gave us an idea to include some physics into the neural network, an approach we called PIN, or Physics-Informed Neural Network. Specifically, we simply added a constraint to enforce positive group contributions for the parameter. As is needed when developing any good prediction scheme, we gathered experimental data for the Parachor from the DIPPR database and split these data into training and test sets. 80% of the data were for training and the rest for testing. As you can see, the resulting parity plot here for both sets. Note that there isn't much bias and the prediction seems adequate. In fact, the test set in red seems to do even better than the training set. Again, what we did is to train a neural network on the blue points and the resulting model to predict the red points. The features provided to the process were group contributions plus the physical constraint that the group value must be positive. Okay, so let's examine these results just a little bit deeper. Over here, we can see, okay, so the results of the non-pin approach right here with 1,000 epochs or epochs, and that's like iterations, updates to the parameters of the neural network. One of the things we can see here is that there's overfitting happening because although we lower this error in the training set, in the test set, the error is higher. So we just needed to reduce the number of iterations, be able to terminate when the test set error started to increase. And so we limited it to 300. Now, one of the other things that we did is we included these physics-based constraints. One of the things that we can see is that it had the worst training, about 0.06 mean absolute error. And when we tested this on other molecules that we didn't use for training, the surprising thing is that this one even did better than the training, okay, 0.05. But this one had the best test results of all of them. Even though it performed worse in training, it performed better on the extrapolation. So we wanted to use this as motivation to say, could this be done for other thermophysical properties as well? And we took a look specifically at normal boiling point. And we did this study with 1,600 compounds. We split it out so that 1,200 were for training. That was 75% of the available data. 240 for validation. That was for hyperparameter optimization. And then 160 of these, or 10%, were available for this testing on data that had not been touched for either hyperparameter optimization or parameter tuning of our neural network. Now, one of the things that we noticed from this is it was very important that we had balanced sets that included contributions in each of these three areas from different chemical families. And so we included some of these, like group contributions from these different groups, chemical family, and then also we included this constraint that the group value must be positive, kind of like a volume parameter for a molecule. Now here's just a graphic that shows this balanced sets for the test, validation, and training set. So here on the inside, we can see the test set. All right, and then on this next circle, this one is our validation set, and then the outside one is our test set. So when we took random samples from each set, we got an imbalanced split between those. Okay, where this is a family of compounds, another family of compounds, and another family of compounds, just for illustration purposes. But when we considered the families of molecules to have an equal representation in each area of test, validation, train, validation, and test, then we got much better results. So up to this point, I haven't said much about the actual groups used in this work. We use the groups proposed by Joback. These are fairly standard groups which don't take nearest neighbors into account, except in a few cases like distinguishing an OH group connected to an aromatic carbon from an OH group on an aliphatic carbon. These groups are easy to parse and understand. More complex schemes which look at nearest neighbors are available, but these sometimes lead to overfitting due to the low number of compounds available to fit some groups. Another reason for selecting Joback is that there are many methods to predict various properties. Besides normal boiling point, there's been others who have developed these groups, so it provides useful comparison and offers opportunities for future work. So we're focusing right here on normal boiling point, but it gives us a potential to explore some of these other properties as well. So here's the parity plots on the results of the physics-informed neural network. Our physics-informed neural network and the Joback group method are shown here on the plot. The results look much different. You can see the pin approach. There's less bias and more accuracy as it stays right along this measured versus the predicted value. Now with Joback, you can see there's a bias here, and then also more severe outliers. So the physics-informed neural network did a better job overall. Let's look at how the effects of including some physics in the neural network versus an unconstrained version, the non-physics-informed neural network. Now the left is the non-pin, normal neural network. The right is the physics-informed neural network with constraints. So this includes constraints on the right, and this one does not. Now you can see here on the train, this is the mean absolute error. So you had fairly similar results here. Now the thing that we want to do is be able to predict on new molecules that aren't measured. And you can see that in the validation set and in the test set, these are much lower when we include the physics information during the fitting process. Okay, let's compare this with some other methods that are out there. Now we did compare it with the Joback method, but there are many other methods that have been proposed as well. And this is what we were talking about, where we've asymptotically kind of limited the amount of accuracy over time of being able to improve these predictive methods. We've kind of hit a point where these standard approaches, where we take structural information and derive a new method, we've reached somewhat of a limit. And with this non-physics informed neural network, we do a fairly good job of fitting on the training set. Okay, and then also with the physics informed neural network, we also do a much better job, a step change improvement versus the other methods. But when we look at this on molecules that have not been used for the training, then we see that the physics-informed neural network is still better. You still don't have kind of the big jump in values, although many of these are the results reported not for a train test split, but APMonitor or others, these are similar to what their training set is, because they use those molecules to be able to develop those correlations. Versus this is a pure predictive method here for the pin on molecules that it has not yet seen. And so it's still encouraging that it's better than all of the other methods, even when those other methods had used those test molecules for their training. So let's just end by summarizing some of the key aspects of creating an effective neural network for predicting properties. More is needed than just adding physical constraints. In fact, there's an entire process that's needed. And we want to start with, first of all, the objective, and that is to obtain better thermophysical properties or relationships between some of these methods, such as the compound structure versus the properties themselves. And so when we go through this list, we see that we get data, we get measurements, and when data is not sufficient, we may use some type of a physics-based simulation. You can get down to quantum mechanics simulations or atomistic or molecular simulations of those molecules to be able to supplement some of the data that isn't there. Then what we want to do is we want to consolidate the data, look at correlations, distributions, pair plots, other relationships between these, do data assessments as well, and look at features. So maybe group contributions are not the right things to be predicting these properties. Maybe there's some other things like chemical family name or other types of descriptors that we could use when looking at a new molecule. Next, we filter out some of the outliers and come up with a cleansed data set. Scale the data and then split the data into train, validate, and test sets. And the validation is for hyperparameter optimization. Now, in the case of this case for regression, we have targets or labels that say this is the property measurement. All right, and then we perform supervised learning with regression. Now, we could also do classification. Maybe the chemical families that we've chosen aren't the right groups to be able to cluster them in. Maybe we can also do some classification. There's many other things that we can do with this whole chart to insert physics-based information as well. Especially here in the data cleansing, where we might be able to eliminate some data that doesn't really agree with some of that physics-based or fundamental information that we shared. Also in the splitting, where we divided it into chemical family names, that was important to be able to take some domain knowledge to be able to help us understand how to split the data to come up with better results. All right, so it requires not only the physics-informed neural network, but also this data engineering. All right, and that has led to this improvement in this case, normal boiling point. Now, we're excited about where this is going to go next. DIPPR and the DIPPR database, there's quite a bit of domain experience in this area, and also a corresponding amount of data for all of these compounds that are there. And so the goal is to be able to create these correlations, not only be able to predict the properties, but in the end, sometimes what we want to do is say, what are the properties that we need? Okay, and then be able to optimize and say, what's the compound that is going to be able to give me those properties? So we can also go in reverse, where maybe we have target properties for a particular application, and then we would go back to the compound, be able to synthesize compounds and simulations based on the desired properties. So there's some exciting new developments, not just with viscosity and normal boiling point, but also be able to predict other thermophysical properties as well. But also, once those correlations are derived or developed, we can start going in the reverse direction, where we can take our pin and be able to optimize to be able to determine what compounds are going to be able to give us those properties. I'd like to acknowledge DIPPR and the fantastic researchers who are involved, also the Office of Research Computing, and we're part of the BYU PRISM Lab as well. We appreciate the many sponsors who have worked with us over a long period of time on developing these methods in physics-informed neural networks, on optimization, process control, and look forward to continuing these collaborations. I also appreciate the organizers of this AICHE spring meeting and look forward to talking with you about some of the questions that you might have, and looking forward to continuing interactions on this project and others. I'd like to take any questions.